This Mastering Physics problem here, we have a pendulum that completes one swing in 1.2 seconds, so that is the period there. We want to know the length of the rod for the pendulum. So we're going to think about the relationship between the length and the period for a pendulum, 2 pi times the square root of L over G. My period is 1.2. I obviously know that G is 9.8, so I can go ahead and solve. I'm first going to divide by 2 pi. Keep in mind that when you do that in the calculator, you need to put that 2 pi in parentheses, otherwise the calculator will divide by 2 and then multiply by pi, which is obviously not what we want. So you should get 0.19 equals the square root of L over G. If we go ahead and solve for that length by squaring both sides and multiplying by G, we get a length here of 0.357 meters. Once it's this answer to 3 sig figs, so that's just going to be my answer, 0.357 meters. For this problem, we have a block attached to a spring with some unknown spring constant that's oscillating with a period of 2 seconds. And we're asked about a bunch of different scenarios of what would happen to the period if we change various parameters here. So this is one of those ones where we're going to want to do our new and our original. So for our original situation, we're going to think about the period of a mass on a spring, T equals 2 pi times the square root of m over k. And I'm not even going to plug in any numbers here. All right, I'm just going to think about how the period changes, and then I'll easily be able to multiply that change by 2 seconds to get my new period. So for this first one here, for my new period, t prime is going to be 2 pi times the square root of 2m now over k. And so the only thing that's really different is this 2 here. Since it's under the square root, I'm going to pull it out, but I need to leave that square root in place. So t prime is going to be the square root of 2 times 2 pi times the square root of m over k. So I just move that out in front, and I find here that this right here is my original period. So I can say that t prime is just going to be root 2 times t, and so that means t prime is just going to be root 2 times 2, which gives me a period here of 2.8 seconds. For the next one, we want to know what happens if the period is halved. So we'll start with the same basic thing. T prime is 2 pi times the square root, but now we're going to do 1/2 m over k. Once again, we can pull out that only difference there, the 1/2, and since it's under the root, it stays under the root, so t prime is going to be the square root of 1/2 times 2 pi times the square root of m over k. This is our original situation here. And so t prime ends up being equal to the square root of 1/2 times t, or t divided by root 2. So t prime is the square root of 1/2 times my original period, which was 2 seconds, and I ultimately get an answer here of 1.4 seconds. Moving on to part C, what happens if the amplitude is doubled? We look at this relationship here, t equals 2 pi times the square root of m over k, and we see that there is no change there for the amplitude. There's no way that that amplitude can affect the period, and we know that conceptually as well. So what is the period if the amplitude is doubled? It's still 2.0 seconds. And then lastly, what is the period if the spring constant is doubled? We'll set up our expression once again. T prime equals 2 pi times the square root of m, but now it's going to be over 2k. Same basic idea. We're going to pull out that 2. That's the only real difference. And so t prime is going to be equal to the square root of 1 over 2. So two things about that. We have to leave it under the square root, of course, and since it was on the bottom here, it needs to stay on the bottom. So the square root of 1 over 2 times 2 pi times the square root of m over k. There's our original, so t prime equals the square root of 1 over 2 times t, same as what we had here, which means that t prime is just 1.4 seconds. Cutting the mass in half or doubling the spring constant ultimately has the same effect. All right, for this next one, we have a graph of an oscillation, and the first question is, what is the amplitude? So we're going to look at when that oscillation is at its peak, which is right here, and we see that that occurs at 10 centimeters, so 10 is going to be the amplitude, the distance from the equilibrium to a maximum, or from equilibrium to a minimum. We would have gotten a 10 if we had looked down below as well. Okay, and then what is the frequency of the oscillation? We first need to determine the period. So period is when this starts repeating itself. So we start here and we go all the way to here when we start repeating ourselves, this point. And so that means that my period is 2 seconds. And so my frequency is just 1 over that period. And so I get a frequency of 0.5 hertz. Technically, these both ask for the answer to 2 sig figs, so you could say 0.50. And for 10 centimeters, technically be 1.0 times 10 to the first power. For this problem here, we have a mass oscillating on a spring. We want to do a number of things. First of all, we want to determine the period. So I'm going to start with t equals 2 pi times the square root of m over k, our expression for the period of a mass on a spring. I know that my mass here is 506 grams, or 0.506 kilograms, and that's what units we wanted in there. So I'm going to plug in that mass in kilograms, divided by my spring constant, which is just 23, and I end up getting a period here of 0.932 seconds. Answer to 3 sig figs, it already is, so just going to be 0.932 seconds. For the second part, determine the maximum speed. The easiest way to do this is going to be to think about energy, right? As the spring oscillates back and forth, it's constantly transferring between spring potential energy and kinetic energy. So I can just think about conservation of energy here. I know that when it's out at that amplitude at a displacement of 12 centimeters, it has all spring potential energy. When it reaches its maximum speed, that's at the equilibrium point, it has all kinetic. So I can go ahead and plug in the expressions. I know for those energies, 1/2 kx squared equals 1/2 mv squared. We'll continue on here, over here, so 1/2 k, which is 23, that's my spring constant, times x squared, 12 centimeters, or 0.12 meters, and that's going to be equal to 1/2 times my mass, which is 0.506, times v squared. Okay, and so I can go ahead and solve here for my velocity. I end up finding that my velocity here ends up being 0.809 meters per second. Lastly, to find my total energy, I either just need to figure out what is my spring potential energy when I'm at my maximum displacement, or what is my kinetic energy when I'm at my maximum velocity. So I'm going to do spring potential energy and say US equals 1/2 kx squared. So my spring potential energy is 1/2 times 23 times 0.12 squared, and I get a spring potential energy here of 0.166 joules. So that ends up being my maximum energy. When we're out at that maximum displacement, all of my energy is spring potential energy, so I know that's my maximum. I also could have calculated my kinetic, 1/2 mv squared, using this maximum speed that I just found in part B, because when we're at that point, when we're at the equilibrium position, all of our energy is going to be kinetic energy, and so if I do this, I end up getting the exact same answer here, 0.166 joules, which would be the total energy. We just oscillate between spring potential energy and kinetic. Alright, for this problem, we have another wave that we're given. We have some questions about this wave. So the first is, what is the amplitude of the wave? So we're thinking about where that wave is, what is its maximum displacement from equilibrium, which occurs right here. Or we could look at its minimum displacement. Either way, it's the distance from the equilibrium point to that point. And so if we look, we see that it's just 6 centimeters. The 2 sig figs, it would be 6.0 centimeters. What is the frequency of the wave? We want to now think about what is our period. Where does the wave start repeating itself? So if we start here, it looks like it starts repeating itself right there, which would be a time of 0.6 seconds. And so if our period is 0.6 seconds, our frequency is just 1 over that. And so we end up with a frequency here of 1.67 hertz. Rounded to 2 sig figs, it's just going to be 1.7 hertz. For the last one, we want to know what is the wavelength of this wave. And so we're going to use that frequency that we just calculated in our velocity equation. Velocity is wavelength times frequency. We know our velocity is 2, our wavelength is what we're looking for, and our frequency is, I'm going to use the 1.67 hertz. And so when I go ahead and do that, 2 divided by 1.67, I get a wavelength here of 1.197 meters. Rounded to 2 sig figs, it's just going to be 1.2 meters. Alright, for this problem here, we have a potentially broken dog whistle with a frequency of 21 kilohertz, which is the same as 21,000 hertz. And you want to test to see whether or not it's broken, but you unfortunately can't hear sounds above 20 kilohertz or 20,000 hertz. And so in order to test this, you have your friend blow the whistle, and you're either going to move towards or away from that whistle in order to be able to hear it, in order to have a Doppler effect occur so that the frequency of the whistle becomes 20,000 hertz or less, to a point where you can actually hear it. So the first question is, in what direction should we ride? We want the observed frequency to be 20,000, okay, lower than the frequency of the source. So in order to reduce that frequency, we want to ride away from our friend, because when we move away, the frequency decreases. So for the second part here, what minimum speed should you ride to know if the whistle is working? We're going to go ahead and actually use our Doppler effect equation and plug in some things that we know. So the frequency observed is going to be that 20,000. We're going to put it right at that upper limit of your hearing ability there. You could leave it actually as 20 kilohertz because there's going to be kilohertz on both sides, and they'll cancel, but I think it's best to always get into the habit of converting because it won't always work out like that. Frequency of the source is going to be 21,000 hertz, and then we can go ahead and plug in these velocities. So the speed of sound is 343, plus or minus your velocity, that's what we're looking for, divided by speed of sound, once again, is 343, plus 0. The velocity of the source, the whistle itself, is not moving. Okay? And so we need to determine whether or not it's positive or negative. In this case, we're decreasing the frequency. All right, so we want that negative there. We don't want the positive, because in order for the frequency to decrease, we need a smaller number on top, and so we're going to be subtracting your velocity to lead to a lower frequency. We're going to go ahead then and solve for this, so we'll divide both sides by 21,000, and we end up getting 0.952 equals 343 minus VO over 343. And we solve for the velocity of the observer, and we end up getting 16.3 meters per second. Rounded to 2 sig figs, it's just going to be 16 meters per second. So for this problem here, we have a friend that is singing a note of 380 hertz while racing towards you at 23.8 meters per second on a day when the speed of sound is 340. So we want to first figure out what frequency you hear, so we're going to set up our Doppler equation. So we're looking for the frequency observed here. We know the frequency of the source is at 380 hertz, and then we can fill in our velocities. The speed of sound that we're given is 340. And we know that in this case, it's the source that's moving at this 23.8. The observer is at rest, so we're going to put that as 0. And the speed of the source is 23.8. We just need to figure out whether it's plus or minus. We know that any motion towards, whether it's the observer or the source moving, results in a higher frequency. So that means that it must be a minus here on the bottom, so we're dividing by a smaller number. In turn resulting in a higher frequency. So we go ahead and calculate that, and we get a frequency observed here of 409 hertz when it's rounded, and so that is our answer, 409 hertz. For the second one, we're going to set up the same equation here, except now we're considering the case where the person that was initially at rest is now emitting the sound, and the person moving is hearing that sound. So we're going to set up our Doppler effect equation Yet again, our frequency of the source is still 380 because the person at rest is making that sound at 380 hertz. What changes now is the observer now is the one that's moving. Okay, so that 23.8 for the moving object, that moving object is now the observer, and the velocity of the source is just 0. Once again, we want to think about whether it's a plus or a minus here, and because it's motion towards yet again, that means that we're going to have a plus here, and so it's going to be 380 plus 23.8 meters per second. So we go ahead and calculate that number. We get an observed frequency now of 407 hertz, 406.6, but rounded to 407. So almost the same, but it does matter whether it's the source or the observer moving, even if the velocity is the same. All right, for this one, we have a graph here, but this is a slightly different graph because we actually see two waves here, and what this is showing is the wave at two different points in time. And so we have a few questions about this wave. So the first thing is we want to know what is the wavelength of this wave. So I'm just going to look at the blue wave, that's the wave of time t equals 0, and see when it starts repeating itself, and I see that happens right here. And so that's going to be a wavelength here of 12 centimeters. Okay, the next question is what is the speed of the wave? And so what I'm going to look at is I have these two times here, okay, and based off of this picture I can figure out how far the wave moves. So what I see here is this point here moves from here to here in that time period, so that means my displacement for the wave is 1 centimeter or 0.01 meters. My time that it takes the wave to move that distance is going to be 0.01 seconds. All right, and I know that my wave here isn't actually accelerating. Okay, so what I can do is I can just set up displacement equals VIT plus 1/2 AT squared. The wave's not accelerating, it's traveling at a constant speed here, and so I can go ahead and solve for the velocity. And so I can say 0.01 equals my velocity times my time, 0.01 as well, which means the velocity of the wave here is just 1 meter per second. If we want to make it 2 sig figs, 1.0 meters per second. Our next question here asks for the velocity of the wave, and so for that I can say velocity equals wavelength times frequency. I know my velocity is 1 meter per second, I just found that. My wavelength was 12 centimeters, or 0.12 meters, and my frequency is what I'm looking for. So when I go ahead and solve for that, I'm doing 1 divided by my wavelength, I end up getting a frequency here of 8.3 hertz. And for this last question, I'm looking for my amplitude of my wave here. So I'm going to go back to my graph here and look at the height from the equilibrium to the peak. So that would be this distance here. And I see that that's a height of 4 millimeters in this case, based off of that scale. And so the amplitude of my wave is just going to be 4 millimeters, and those are the units already given. For this one, we have a standing wave here on a string that's 1.1 meters long, so that's my distance here from between the two ends, 1.1 meters, and I know my wave speed. I want to find my frequency. So what I'm going to do is I'm going to think about how many wavelengths I have in that 1.1 meter space. All right, and so if I go ahead and count them, there's 1 wavelength, there's 2 wavelengths, there's 3 wavelengths in that 1.1 meter space. So that means that each wavelength is going to be equal to 0.367 meters. Okay, and I just got that from doing 1.1 divided by 3 because I know that I have 3 full wavelengths in that 1.1 meters. So once I have that, I can go ahead and calculate my frequency based off of that, and I can do that by saying velocity is wavelength times frequency. So 50 meters per second equals 0.367 times my frequency, and I end up getting a frequency here of 136 hertz. And so that is my answer. Alright, for this one, we want to calculate the three longest wavelengths for standing waves on a 280 centimeter long string fixed at both ends. So we know that for a string fixed at both ends is the same thing as being open, open, or closed, closed, and it obeys the pattern L equals m lambda over 2, where m, our harmonic number, is 1, 2, 3, so on. Okay, and so I can go ahead and set up an equation and solve for those first three harmonics, all right, those first three values of n. So we'll start with m equals 1, and so in that case our length is 280 centimeters, which is really 2.8 meters, so I can say 2.8 equals m, which in this case is going to be 1, times lambda over 2, and so I get that my wavelength is going to be 5.6 meters. So that's my first wavelength there. For my next one, I'm going to have the same basic setup here. My m is just going to be 2 now, and so it's going to be 2.8 equals 2 times lambda over 2, and so in this case my wavelength is just 2.8 meters, equal to the length of the string. And for the last one, when m equals 3, that third harmonic, I'm going to have 2.8 equals 3 times lambda all over 2. And so when I go ahead and solve for lambda in that case, I end up getting an answer here of 1.87 meters. So those would be my three wavelengths, lambda 1, lambda 2, and lambda 3, representing the first three harmonics. So we would just put in those three answers. For the second part here, we're told that the frequency of the second longest wavelength is 60 hertz, and we want to know what the frequency is of the third longest wavelength. And so for that, I'm going to think about the fact that velocity is constant for both of these waves. All right. In order to change the velocity, we have to change the medium, and since they're on the same string, they have the same medium, and therefore they have the same speed. So I'm going to think about that second longest wavelength and say velocity is wavelength times frequency. Okay, I know my wavelength here is 2.8, and my frequency is 60 hertz. So when I go ahead and calculate that velocity, I end up with a velocity here of 168 meters per second. I can now use that velocity to figure out what my frequency is going to be for the third wavelength. And so I can say velocity equals wavelength times frequency yet again. 168 equals the wavelength for my third one, which is 1.87, times the frequency. And so I end up getting a frequency here of 90 hertz. Okay, it should obviously be higher because it's a smaller wavelength. So we're going to have a higher frequency to maintain the same velocity. Alright, for this problem here, we have a violin string with a length of 32.8 centimeters, or I'm just going to go ahead and convert this now, 0.328 meters. And that particular violin string plays a note of 440 hertz when played without fingering, meaning that we're using the entire length. So we want to know how far from the end of the string should you place your finger to play the note 523 hertz. Once again, we remember that velocity is constant for all the waves on this violin string, so we can use that to our advantage and solve for our velocity. But the first thing we want to do is figure out our wavelength. And so we're going to think about L equals m lambda over 2. That's our equation for a string that's fixed at both ends, like this violin string. The thing we want to also keep in mind is this 440 hertz that we hear. That tone is the fundamental frequency, which means m is equal to 1. So I'm going to go ahead and say the length of my string, 0.328, is equal to 1 times lambda all over 2. And so I find that my wavelength here for that fundamental frequency is 0.656 meters. Okay, I can now take that and I can solve for my velocity because I know my frequency here. So I can say that velocity equals wavelength times frequency, 0.656 times my frequency of 440 hertz. And so I get a velocity for this wave of 288.6 meters per second. Okay. I now can think about this new note that I want to play, the 523 hertz, and so I can take that velocity and use that exact same equation, but just change around the frequency. so 288.6, equals my new wavelength times my new frequency, 523. And so I get that my wavelength for this new note is going to be 0.552 meters. Okay, and now I can use that to figure out what the length of the string will be, going back to this equation that I started the problem with here. And I can say L equals m lambda over 2. It's the exact same m because we're still talking about the fundamental frequency. The difference now is I know my wavelength is 0.552, and I'm solving for the length of string that's needed to produce that note, and I get an answer here of 0.276 meters. In centimeters, that would be 27.6 centimeters. Alright, for this problem, we have an organ that we want to play a note of 27.5 hertz, which is a very low note, and we want to know what length pipe we need to play that note. So the first thing I'm going to do is I'm going to take that frequency that I have and the speed of sound that I know, 343 meters per second, and I'm going to use that to solve for the wavelength of that note with a frequency of 27.5 hertz. And so when I do that, I find that the wavelength for that note is 12.47 meters. So pretty long wavelength because that frequency is so low. So the first question asks what length open-open pipe would be needed to play this note. And so I know that open-open follows the pattern, L equals m lambda over 2. I'm playing the fundamental frequency. That's the frequency we actually hear. So my m is 1 here. I know my lambda is 12.47. And I just divide that by 2 to get the length of pipe needed in order to play that note. And I get an answer here of 6.24 meters. Okay. For the second part of the question here, we now have an open-closed pipe. And I want to know what length pipe would be needed for that in order to play that note. So same basic idea. I'm just going to use my other equation for the open-closed pattern, m lambda over 4. My m, once again, is still 1 times that wavelength, 12.47, divided by 4, and I end up getting an answer here of 3.12 meters. So obviously a much shorter pipe would be needed if we use that open-closed type of pipe.